Hello, everyone. Thank you for attending my presentation. My name is Yuxiang Guo from Nanyang Technological University. The title of my talk is the Pancharatnam-Berry phase and the non-local control of light dissipation. We have been working on the interaction of the quantum light with coherence perfect absorption process by using a thin metamaterial placed in a single photon interferometer. We have demonstrated that the photon coupled to the plasma can be varied from nearly perfect transmission to perfect absorption. Furthermore, using the polarization entangled photon pairs, we have demonstrated a non-local interaction of light. With this absorber, we can prevent or auto absorption of the remote photon. But all these two experiments, the dispersion is dependent on the position of the field locally in the interferometer. Today's talk, I will report a non-local control of light dissipation by exploring the strong phase correlation in the entangled photon pairs. The geometric phase will be employed for non-local phase control in our experiment. What's the geometric phase? In 1984, Berry reports that when a system is transported slowly around a circle, the system will acquire an extra phase in addition to the dynamic phase. And this additional phase depends only on the geometric path taken by the system. And this phase factor is called the geometric phase. The process to generate geometric phase relying on two key points, adiabatic approximation and the cyclic evolution. The geometric phase on the adiabatic approximation is named as the Berry phase. With time, the concept of geometric phase has a fundamental and broad applicability in several areas of physics. And a number of experiments were done to observe this geometric phase. Here's a list that well know the manifestation of this geometric phase. Geometric phase in optics. If the polarization state of the wave changes during propagating, the wave may acquire an extra contribution to its phase, which is in addition to the change in its dynamic phase. This phase was first discussed by Pancharatnam, and it's an example of geometric phase in optics. Here, this is a Pinchari sphere. Its surface describes all the possible pure polarization state of light. The polarization state of the wave and its evolution can be described as a point and its trajectory on the surface of the point Pinchari sphere. For cyclic evolution of polarization, from the A to B to C and then back to A, this trajectory of the polarization is a closed curve, and in this case, the phase shift arriving. We name it Pancharatnam-Berry phase, and this phase is equal to the half of the solid angle enclosed by this closed curve. Pancharatnam-Berry phase will be employed in the entangled photons to realize the non-local phase control in our experiment. The ideal photon will pass through this combination of wave plate, which induce a cyclic evolution of the photon polarization. For the horizontal linear polarization, the first quarter wave quarter wave plate convert it into left circular polarization, and the half-wave plate had the effect of flip the handedness of the circular polarization state from left to right circular polarization, and the second wave plate convert right circular polarization back to the horizontal linear polarization. This flip of handedness of half-wave plate is independent of the orientation of the half-wave plate. However, the outgoing beam acquires additional global phase phi, and that is 2 times of the angle of the rotation of the half-wave plate. This actual phase factor is exactly the geometric phase. Horizontal and vertical polarized component acquire phase of opposite side, the plus phi and minus phi. Finally, the Pancharatnam-Berry phase changed the initial state by introduce the phase difference between the component of this 2 photon wave function. And this state shows that 2 photons have strong phase correlation, which make this non-local phase control possible. When the phi equal to 0, it's a symmetric polarization in tangle state. And phi equal to half pi, the 2 photon state shifts to the anti-symmetric state. In the following discussion, we will notice that this symmetry of wave state affects the absorption rate of the absorber. Okay, coherent perfect absorption with subwavelength absorber. The simplest structure of this coherent perfect absorption is a 2-port linear system with absorption sheet thinner than the operation wavelength. Each input beam is partially reflected and partially transmitted. Some of its energy can also be absorbed into the medias. With coherence beam incident from both sides, the reflected and transmitted wave can destructively interfere on each side, result the perfect absorption. This absorption can reach 100% coincided with anti-node of this electron field. And if the absorption if the sheet is located at a node of electric field, and then absorption vanished. And this sensitivity of the coherence perfect absorber to the input waveform provide the opportunity to exactly control light scattering and absorption. How about this coherence perfect absorption in quantum regime? In the context of this paper about loss beam split, the possibility of achieve complete absorption of single photon has been understood, where the loss beam split is opaque or transparent for the standing wave of different symmetry. We fabricate 2 kinds of the absorb. One is a nanostructured metamaterial, freestanding thin 50 nanometer thick golden film was nanostructured with this split ring and generate partially absorption and transmittance. This is the match this requirement at wavelength 8 to 10 nanometer. And the second is this mechanical nano layers. The thin 5 nanometer chromium is deposit both sides of this silicon nitrogen thin film with the thickness half wavelength, and this also achieve the transmittance and reflect 25% and absorption 50%. Okay, the experiment. In the experiment, the polarization entangled the state is generated through the spontaneous parametric down-conversion process in the nonlinear BBO crystal. By applying this Pancharatnam-Berry phase control to this idle photon, the dissipation experienced by the second this single photon can be switched on or off. The single photon is sent to the interferometer where it excited the standing wave in the middle of the interferometer. The standing wave interaction with the thin absorber. If the absorber is at the antinode of the standing wave, it is interface with the symmetric mode. Strong light matter interaction take place and the photon is fully absorbed. If the absorber is at node of the standing wave, its interface with the anti-symmetric mode, the photon is fully transmitted. We perform 2 photon polarization sensitive measurement. The idle photon pass through this polarizer, the orientate to at 45 degrees and is detected by a single photon detector. And the signal photon is detected on both sides and of this absorber. The polarizer placed in front of this corresponding detector are oriented vertically. And the halfway plate inside this interference set to 45 degrees for switching the horizontal and vertical beams. Finally, here we show remote control by measuring the coincident count between the signal photon detector and idle photon detector. This is as a function of the Pancharatnam-Berry phase. Thus, the probability of the single photon dissipation by the absorber depends on the Pancharatnam-Berry phase applied to the idle photon. And here is the dependence of the total coincident counts on this geometric phase is in a good agreement with the expect behavior and with well-distinction regime of strong and weak light dispersion. In summary, we have demonstrated that Pancharatnam-Berry phase allow non-local control of the entangled photon, and the non-local phase control of photon dissipation is demonstrated. And by replace the absorber with the system able to support and store the quantum coherence, advance the protocol of light matter interaction may be realized, including the remote control of the quantum memory or quantum network. Okay, I end my talk here. Thank you for your attention.